Hello, this is Subbarao Kambhampati, and I'm going to be talking to you today about our blue sky paper, Symbols as a Lingua Franca for Bridging the Human AI Chasm in Explainable and Advisable AI Systems. This is a joint work with my students, Sarath Sreedharan, Mudit Verma, Yantian, and Lingua. So let's get started. So we are increasingly surrounded by the AI systems, and it's critical that they are explainable to us and are advisable by us. The explainability and the advisability must be on our, that is, human terms. We really shouldn't have to debug AI systems to interpret them. After all, it will be a pity if all the progress in AI results in us humans going into the incomprehensible land of the AI systems and spending time there. So we really want them to communicate with us on our terms in being explainable to us or taking advice from us. And the central argument of this blue sky paper is that the AI systems must support a symbolic lingua franca to communicate with humans in the loop. And what we'll try to do is kind of explain what such a interface would look like and what are the challenges in making that happen. As soon as I said the word symbols, you might start thinking about the current interest in neuro-symbolic systems. And I want to upfront sort of separate two orthogonal motivations for neurosymbolic AI and sort of point out that our motivation is the second of them. So, in particular, you could be interested in neurosymbolic AI because you believe that AI systems would need internal symbolic reasoning, probably symbols as abstractions of their lower level signals, and reason about them, and then that is required for efficiency and scalability. Now, the jury on that is still very much out. And I'm not going to take any stance on that particular motivation in this talk. The other motivation for neurosymbolic AI is that AI systems, irrespective of the way they do their internal processing, should interact with humans in symbolic terms, mostly because we humans are used to symbolic terms. And so the alternative, after all, would be exchanging some sort of space-time signal tubes with pointing explanations and advice. I'll talk about it later. And that's just way too much of a cognitive load for humans. So this symbolic lingua franca for explainability and advisability is the main argument of our paper. And of course, this may well be in addition to other modalities of communication, but the central point is that we do need a symbolic interface, irrespective of whether or not the AI systems are actually using internal symbolic reasoning. I should also point out that even if AI systems are using internal symbolic reasoning, that there's no guarantee that the symbols that they have abstracted out would be making any sense to humans in the loop. Whereas the symbolic communication interface sort of requires that the system should support symbolic communication in terms of symbols that make sense to humans. Okay. So having said that, so the talk overview is the following. I want to kind of give you some idea of mental models and their central role in explainability and advisability, and talk about the new challenges that come when, in fact, the AI systems and the humans in the loop have basically no shared vocabulary. And how do you support explanations and advisability there? And then at that point, I will motivate the explainability and advisability in terms of symbolic interfaces, explain what that would mean, and then give you an idea of the details by talking very briefly about three recent papers from our group. One is an ICLE 2022 paper, the other is a NeurIPS 2021 Spotlight, and the third is a AAAI 2022 workshop paper. And then I will go into research challenges involved, sort of generalizing over these case studies, research challenges involved in making this sort of a symbolic interface feasible which and talk about the collection of the initial concept set, grounding, and vocabulary expansion. And I'll end with a summary. So let's get into the mental models. So what does it take for AI agent to show explainable behavior in the presence of human agents? We've been looking at this in our lab for several years now. And in fact, our central thesis has been, and it's sort of consistent with the psychological literatures, that explanations and advisability are very much tied to managing mental models. As you know from even something as simple as Salient test, that we know that humans have developed this ability to mental model others and use that as a significant leverage in providing explanations or taking advice from them. So in particular, in our lab, we specifically looked at this robot model MR, humans model of the task MH, and then the robot has an approximation of the humans model, which will be MHR, and similarly, human has an approximation, an estimation of the robot's model, which is MRH, and providing explainability from the robot or the AI side is essentially being consistent with what the human thinks of the robot, which is MRH. So in fact, we've done significant work on this in providing explanations and providing explicable behavior with this sort of view of MHR and MRH. And there's actually a book that just came out this month, actually in January, on explainable human AI interaction, a planning perspective that you might be interested in looking at. Now, the interesting thing is that significant amount of that work was done basically assuming that there is some sort of a shared vocabulary. Turns out that even when there is a shared vocabulary, the models could be different. So the preconditions and effects of the models that human thinks, the requirements the human thinks are there for tasks or the actions might be different from what the robot knows, and vice versa. But things become even more complex when in fact there isn't even any shared vocabulary. An agent might actually be using a learned model or an inscrutable simulator. And so then what would you do in those cases? So what I'm going to be talking about is explanations in the absence of shared vocabulary. So here, ultimately, you might just say that the lowest common denominator between the humans and the AI agents would just be raw signals and data, and providing explanations or taking advice in terms of those raw signal and data, which I would like to think of as space-time signal tubes, especially if you have sequential decisions, is just a very primitive form of interaction. Surprisingly, and probably unfortunately, XAI literature mostly focuses on that sort of space-time signal tubes. And in particular, kind of pointing explanations is the only thing that has become popular in the machine learning literature, where the system has a very different representation. Maybe starting from pixels, it develops its own internal representations, which have nothing to do with the humans' representations. And so that's kind of, unfortunately, not as good from a human perspective, because pointing explanations are quite hard to comprehend for us humans, not only in terms of them being unwieldy, in the sense I have to kind of provide you like a video of my life with some annotations on it to explain any of the decisions I have made. But they're also really hard to comprehend for the humans in most cases. So humans instead develop a shared symbolic vocabulary and exchange symbolic explanations where possible, and come down to pointing explanations only when the vocabulary becomes inadequate, and use that as a sign to expand vocabulary. This approach sort of works particularly well for all of our explicit knowledge tasks, but we also use it for mixed and tacit knowledge tasks. Think of, pick and roll in basketball, which is a pretty tacit knowledge task, but then you have symbolic terms to describe things there. So what we basically are arguing in this paper, Blue Sky paper, is that we'd like to advocate a symbolic interface layer instead to support the communication between the human and the machine irrespective of whether or not the machine is actually using internal symbolic processing. So that gets me to the second part. So the use case for the symbolic layer for us is that we want to use the shared vocabulary to build an approximate symbolic representation of agent model that is sort of surfaced to the user as needed and on demand. And this symbolic model kind of aims to capture the human's understanding of the robot model, for example, the MRH that I mentioned earlier, and it can thus be used as a basis for any human-robot interaction, for example, that depends on MRH, such as model reconciliation-based explanations. In particular, we can use this for generating explanations as well as accept advice from user. So in terms of generating explanations, we can use the symbolic model as a basis for explaining any decisions made by the system. We can directly leverage the model in the context of our earlier methods like model reconciliation and other explanation methods developed for symbolic models. So the symbolic model being an approximation of the underlying system also means that these models might actually be noisy and approximate, and you need to be tolerant to that. And so we sort of need to provide this ability to handle noisy approximations. I want to kind of illustrate this in terms of some work that we have done in our lab that just is going to be appearing in ICLAY 2022. Here is basically, we're looking at like a system which is working on like a Montezuma's Revenge, which is a pixel-based, RAM state-based Atari game. And the human in the loop is trying to interact with the system, asking questions as to why it did certain kinds of decisions and so on. And so, for example, the human might be providing a file as to why exactly do you take this decision as against a different decision. And the machine might well have come to its reasoning based on its internal RAM state representations, which won't make sense to the humans when providing explanation in those terms. So instead, it will wind up providing explanations in terms of missing preconditions or abstract cost functions that it learns on demand based on the file. So this is sort of like a local symbolic approximation of its reasoning that is done on demand. It's sort of like the older work like Lime, except in this particular case, we are doing it for sequential decision problems. And we are kind of using these preconditions and effects that come from an agreed upon symbolic vocabulary between the human and the machine. And then we also can extend this to consider the confidence level for the symbolic models and how from that the confidence level for the explanation comes in. Okay, now turning to the accepting of the advice, so the humans can directly update the model, should be able to directly update the model to drive system behavior. In fact, McCarthy said one of the main goals of AI is that the system should be advisable, but he meant it as advisable by us humans, not by debugging like byte level code or like a neural network activations, but by actually providing symbolic advice. And this, we want to provide this modifications are made and constraints applied to the symbolic model. And those are translated into a form that can then be used by the AI agent in its processing. And of course, in fact, we can even use the symbolic model as a basis to interpret even non-symbolic advice, such as demonstrations, as we'll show in a minute. That also can be sort of an advantage of the symbolic models. So here, the examples that we have are, for example, there's a NeurIPS 2021 Spotlight paper where we look at how humans can advise a reinforcement learning system by correcting its errors and then providing perhaps additional information about their preferences and so on. Now, they can do it. In fact, the traditional model is that the humans would do it at almost the pixel level or at the level the machine is working. But that's just way too cognitively high load for the humans. Instead, we actually support in this NeurIPS paper, we support like a symbolic interface, an object-oriented interface that the humans get to use to talk about why certain decisions that the machine made are wrong, and provide an explanation for their recommendation in terms of objects that are in the scene, for example, they might say that the braking action is the correct one because there is a stop sign in the particular scene right now. And this sort of allows for a much faster and more fluid interaction between the humans providing advice to the machines. And we have actually shown that this improves quite significantly the amount of time that people have to spend in training the reinforcement learning system in the human in the loop reinforcement learning. Like I said, there's details are available on this new RIP Spotlight paper in 2021. One other interesting part of this work is that once the humans provide this symbolic advice, the machine then converts that into the pixel level by essentially looking at the objects that they have mentioned in their advice, and then it expands on this advice essentially by augmentation, wherein it keeps those objects and the pixels for those objects constant and perturbing the rest of the image. So this is like additional internal details about how the machine winds up operationalizing the advice that the humans have. That's the context-aware data augmentation. Then finally, we can also interpret ambiguous human demonstrations in terms of shared symbols. There's a paper that is being presented at this workshop on RL in games by Yantian called SRL-FD. This system essentially looks at the human demonstration with the understanding that the humans are probably demonstrating with respect to some symbolic concepts they have in their mind, and that bias significantly reduces the ambiguity in the human demonstration. That's worth pointing out. So now coming to the research challenges, I'm very quickly going to point out that there are going to be a collection of the initial concept set. Again, we have done this in the work that we have done, and the challenges here we are talking about are the more generally, how do we expand this, collecting the set of propositional and relational concepts. And sometimes this can be done at a task specific level. Sometimes it may be possible to do it by leveraging systems like scene graph analysis, where essentially the concepts are common across multiple tasks. These concepts can also be mined from domain-specific databases. Then the other interesting part is the grounding of the concept set. So essentially different humans, mostly the humans, mean certain specific signals and the raw level data patterns in terms of their symbols. And the machine has to kind of learn that by learning a classifier, and use that. And in fact, that's what we wind up doing both in the iClair paper as well as the NeurIPS paper. And then the challenge 3 is the vocabulary expansion. Here, basically, we actually need to be able to realize, the system needs to realize if, in fact, the vocabulary that it has agreed upon with the humans is complete enough to actually exchange the explanation, and if not, be able to expand the vocabulary as needed. When the vocabulary has to be expanded, there can be two sources of incompleteness. One is the user forgot to specify the concept. The other is the user's vocabulary does not even include the equivalent concept. In the former case, we develop new techniques that are able to efficiently query the human for previously unmentioned concepts. In the later case, it's really machine teaching the humans. There's some interesting work, for example, by in DeepMind with Bin Kim and other people involved, which try to kind of look at what AlphaGo might have based its decision on by essentially teaching some symbolic concepts to humans. And that's the kind of thing that you will end up having to do in vocabulary expansion, where the humans don't even know the missing vocabulary. In summary, we argued that the AI systems should support a symbolic interface for communication with humans, independent of whether their internal operations themselves are done in symbolic means. We discussed the research challenges in establishing such a symbolic interface, collecting initial concept set, grounding the concepts, and vocabulary expansion, and in particular illustrated these potential solutions by discussing recent case studies from our group, Black Box in iClair 2022, Expand in NeurIPS 2022, NeurIPS 2021, and Sir FD in AAAI 2022 workshop. In the long term, symbolic interface might morph into a symbolic persona for the human AI, for the AI systems. That leads to an intriguing question. Will the internal symbolic reasoning versus external symbolic interface disappear when the machine sort of moves itself into the symbolic persona? Certainly, language developed by humans that we developed for interhuman communication has arguably changed the very way we think. As Wittgenstein says, the limits of my language mean the limits of my world. But I will leave that as a long term question that you can ponder. And thank you for your attention.